Good afternoon, everyone. So as Matt said, my name is Dagnelie. I am a software engineer at Delphix. This is my 10th developer summit. I'm really happy to be here. It's been really awesome. Thank you. It's been really awesome to get to be a part of this community and come here for so many years and get to interact with these people and share this time with all of you. So that's been really great. I've given a couple talks in the past about redacted send receive several years ago, and then about Metaslide performance a couple years after that. And today I'm going to be talking to you about shared log pools, which are a project that I've been working on for a little while. So we're going to start with some technical background so that you understand all the parts of the system that you need to in order to understand the new feature. So we're going to start with the ZIL. So ZFS, as we probably all know, is a tree-based file system. So when you update some data, you have to update the parts of the tree above it, and that can lead to some overhead. And so one of the things that ZFS does to reduce this is it batches data into transaction groups. Transaction groups are an efficient mechanism to reduce this overhead, but they're more efficient the bigger they are. So they tend to be a little bit infrequent and they tend to contain a lot of data. So they take a little while to process. One of the jobs of a file system is handling synchronous writes. There are two basic flavors of writes. There's asynchronous writes, where a program comes to the file system and says, please store this data on disk. And then it goes back and keeps doing things. And the file system persists the data whenever it gets around to it. And then there's synchronous writes. For synchronous writes, the program says, persist this data to disk. And then the file system doesn't return control to the program until the data is actually on stable storage. So it's important for the synchronous writes that you have very low latency because your throughput is directly tied to how fast you can complete these writes. These are very commonly used in certain workloads. For example, databases use a lot of synchronous writes because they need their consistency guarantees to be met. And in order for that to happen, they need to actually know when the data is persisted on disk. And so there's sort of an anti-synergy between these two things, right? You want these very low latency synchronous writes, but at the same time, you want transaction groups to be big so that you can be efficient and sync out lots of data at the same time. And so ZFS's solution to this problem is the ZIL, or the ZFS intent log. It's a per file system or per data set data structure that is a chain of ZIL blocks. And these ZIL blocks contain the synchronous writes and other operations that need to happen synchronously. And they're chained together. The ZIL is not a long-term storage solution. When you write data to the ZIL, that's not where it's going to stay forever. Data is only read from the ZIL when something goes wrong. So if there's a power outage or your kernel crashes or something like that, that's when we actually use the ZIL. Otherwise, the data gets synced out normally as part of a transaction group, and that location is where it will actually be read from in the future when the user wants to read that data. So let's talk in a little bit more detail about how the ZIL works. So a synchronous write comes in, we need to persist it to disk. In order to persist it to disk, we need to allocate a block. When you allocate a block, we can do that from our in-memory data structures, but you also have to write out that you allocated that block onto the disk so that we don't overwrite that data later. But if we wait for that allocation to sync, then we have to wait for a transaction group to sync out. And now we're waiting for a whole TXG in order to do a synchronous write. And that's terrible for latency. So the way we solve this problem in the ZIL is that the blocks are chained together. Each ZIL block points to the next ZIL block in the chain. So you can always use this chain of blocks to recover all these allocations and know where all of your data is stored on disk. And then after you've done this sort of ZIL allocation and written the data into it, when the transaction group with that data does sync out, we advance the head of the ZIL chain. So we move the pointer in the file system from the first block to a later block once all of the data before that block has synced out. Because all the data in the ZIL is in order, in the order that we created it, at least at a transaction group granularity, you can't lose data this way. When you move the head forwards, all of the old blocks are guaranteed to no longer have data that isn't persisted on disk already. So the head of the chain moves forwards, all of the old blocks can be freed, and the data in them is now persisted in its proper location on disk. So let's talk about the case where something does go wrong, where we actually do need to read from the ZIL. So your kernel panics, your power goes out, something goes wrong, your system reboots and comes back up. So as I said, we have all these ZIL blocks that we allocated, but we couldn't persist the allocation to disk yet because we didn't manage to sync out the transaction group. So we need some mechanism to find all of those blocks on disk and then actually mark them as allocated in the space maps so we don't reuse that space and trample on the data. And so the process for that is called ZIL claim. And so the way this works is that on import, we go over every file system in the pool. And then we iterate over the chain for the file system and mark each block in the chain as allocated. So that way we don't trample on the space that we used for the ZIL. The next part of the process is actually using the data that's in the ZIL so that we get the data that the user wrote back. And that's the job of ZIL replay. This is a separate step that happens when you actually mount an individual file system. When you mount the file system, you iterate over the chain for that file system, and then you apply each record in each of the blocks. You can have several writes coalesced into a single block for efficiency reasons. And so because the data is all in the ZIL already, right, it's still in the ZIL chain, you can just apply these as normal asynchronous writes. And when a transaction group syncs out, you'll get to advance the ZIL chain the way that you normally would, and the system will go back to functioning the way that you intended it. And so that's how we use the ZIL to recover from failures. So the next thing to talk about is the slog. So I mentioned earlier that we allocate these ZIL blocks on your disk. And that sort of leaves the question of where do we do these allocations? Where do these ZIL writes go? So the sort of naive, simplest solution is that they just get stored with the rest of your data, right? On your normal VDEVs, mixed in with the rest of your stuff. But there are some problems with that. The first problem is that as your disks fill up, fragmentation increases, the amount of like big free chunks goes down, and your biggest free chunk gets smaller and smaller. And ZIL blocks tend to be a little bit big because you want to try to get as many writes out as possible. And so you want to try to batch things together. And so it can be hard to find good places to allocate this data. And even if you can find good places to allocate the data, even if you have lots of free space, your normal disks are like being used by the rest of your reads and writes. You know, you're doing reads to them, you're doing writes to them. And so there's a lot of other traffic going to those disks that might make your synchronous writes slower. Plus, if you want your synchronous writes to be fast, you probably don't want to use spinning Rust. You want to use Flash or NVMe or other sort of advanced storage technologies. But now if you have to make your whole pool out of those more expensive disks, it's going to be a lot more expensive to store the same amount of data. There's a few ways that you can mitigate some of these problems. So the embedded slog was a feature that was introduced a few years ago to help with the allocation part of the problem. And so the idea there is that there's just a separate one metaslab in each VDEV. There's a segment of each disk that is prioritized for the ZIL allocations. So that way you basically always have some of this pristine space where you can reliably do these allocations and you can quickly and reliably find the space. But this doesn't really solve the problem with, you know, having other traffic to those disks or needing more expensive disks to get really good performance. So it solves one problem, but not the others. If you want really good ZIL performance, you need a slog device or a separate intent log device. And the idea here is that it's just another disk that you have attached to your pool that is only used to store ZIL data. So this is the way that you get the best performance, right? You have this separate device. You can make it a single, very fast device that doesn't need to be that big because it doesn't need to store that much data. The downsides are that there's more administration work. You now have another device that you need to manage. You probably want it to be mirrored if you really care about your data, because otherwise, if you lose that disk and have a power outage, you've lost all of the stuff that's in your ZIL. It's probably a pretty expensive device because, you know, it's another device that you have to buy and you want it to be high-end storage. So there's trade-offs for using this slogs versus other devices, but generally it's the sort of best performance solution. And it's how you solve the problem if you really care about synchronous write performance. So that's the ZIL and the slog from a technical perspective. Now we're going to talk a little bit about the context that led to the work that I was doing. So when most of us interact with ZFS, we have a single system with a single storage pool with a bunch of disks in it. And those disks might be mirrored or RAID-Z or whatever. But there are some situations where you might want to have multiple storage pools on a single system. And I'm going to talk about some of those use cases to kind of motivate what's coming next. And so one context is if you want to be able to move data from one system to another system. And one easy way to do that is if you have like a storage area network or a fiber channel backend that you're using to actually host your physical drives. And so one setup that you could reasonably have in that case is that you have a bunch of different pools serving a bunch of different data that all get their actual storage from the SAN. And you know, they're all busy doing work, but then one of your pools ends up getting a lot more traffic than it previously did. And so you want to move it to a new virtual machine or physical server in order to actually get better performance for that pool and the other pools sharing a system with it. So you can actually move the data from one system to another or migrate them back together if you have ones that start demanding less performance. So there are reasons why you might want to be able to move these systems around. And that's a reason why you might end up having multiple pools on one storage system. Another context that people use multiple pools in is for fault isolation. And this is particularly common for data caching. So if you have a really big cache, you want to store lots of data in it. You don't want to necessarily use mirroring or RAID-Z because you want to get the most storage for your disks. But also, you don't really care if you lose some of the data because it's just a cache. You can always fail over to whatever's behind the cache and fetch the data normally. So you want to have this sort of isolated fault behavior. So you can actually have a separate Z pool for every disk. And that way, if one of the disks dies, all of your other data stays accessible. There's administration overhead to this, but it turns out that a lot of caching software already supports this kind of layout because if you aren't using ZFS, you already have one file system per disk. And so a lot of the caching solutions already support this sort of multiple map point approach. So this is another context in which people actually have several Z pools on one system. And then there's a bunch of other cases, right? You might have multiple pools on a system because you're moving data from one to the other so that you can then physically move some disks from one place to another. If you want to do like a sneaker net approach, if you don't have good networking between two locations and you want to move data around. Or if you have data with very different performance or redundancy requirements, you don't necessarily want to mix it onto one pool because there will be mismatches where, now you have bulk data that you don't want to store on expensive drives, or you have, high performance data that you don't want to store on spinning Rust. And so you might have multiple pools for those reasons as well. And so this picture sort of shows you what the problem is going to be. Let's say you have lots of storage pools on your system. And for a bunch of them, you actually care about the synchronous write performance. You want to give them slog devices. And so now you have a slog device for every pool that you're using. And maybe you don't want to use like a whole physical disk for every single one of these. So you have like one disk and you partition it for some of them. And so now we're starting to get into some thorny administration problems. How do you do capacity planning? How much of the disk should each pool get? What happens if one of your pools starts to get more demand than it used to? Do you need to like buy more disks and attach them? Can you repartition? And what happens when you add or remove pools? Are you going to repartition all of your slogs now? Are you going to buy new slogs just because you had one new pool come onto the system? So we've created sort of all these administrative problems if you try to have many pools with slogs on a system. And the insight is that this is why Z pools were invented in the first place, or one of the reasons. The goal was to be able to just pool all your storage, and then it would get used by the file systems that need it, and you didn't have to think about that mapping from disk to file system. ZFS would handle it for you. And so the solution to the problem is the shared log pool. And the idea is basically that it's just a pool of slog devices. And then you can have client pools that talk to the shared log pool and actually use it as their slog. So you can see in the diagram here, we have all of our pools from before, but now instead of having their own slog devices, they talk to the shared log pool, which provides slog capabilities for all of them. It's important as part of this project that we keep performance very close to the way it would be with dedicated slog devices, right? Because if you can't do that, then you're starting to introduce big trade-offs between, should I use slog devices? Should I use the shared log pool? And it starts to make it a much more thorny question. So we really want performance that's just as good as we had with slog devices. And then also we want all the simple administration benefits that we get from, using ZFS and having storage pools and having that sort of relatively simple administration of lots of disks. So let's talk about what a shared log pool is. And the easy way to start with that is how you make one and how you use one. So a shared log pool is, under the covers, basically a normal Z pool. And from a user perspective, it's basically a normal Z pool with a couple caveats. One of them is it doesn't have any file systems, which is a little unintuitive for a storage pool, admittedly. But the reason for that is that we don't want you to be able to store user data in this pool. It's really intended just as a space to store the ZIL data. That's the way it's designed right now. That could change if people really feel that it should be able to store user data, but this was what made the most sense as part of the design. And then it's marked as a shared log pool with a flag in the config or in the pool config. And when you create the pool, a new data structure is created, which is called the chain map. And I'll talk more about what that data structure is and why it exists and what it does later. But here you can see sort of what it looks like to create a shared log pool. There's a new flag to zpool create, the -L flag. And when you create it, it looks just like a normal pool, right? You've got the name, you got the size, you got all your disks, everything looks good. Let's talk about the client pools, the pools that actually use the shared log pool to provide slog capabilities. Again, very normal zpool, except that they don't have physical slog devices. There's no actual disks, there's no embedded slog. And so one consequence of this is that you either have a shared slog or you have physical slog devices. You can't have a hybrid approach where you have some slog devices and a shared log pool on the same, attached to the same pool. You get to a lot of thorny technical issues if you try to mix the two approaches. So it's all physical or all virtual, no hybrid approaches. The client pools are marked as depending on the shared log pool. So in order to import your client pool, you have to have the shared log pool imported. If you try to import it without the shared log pool, it'll tell you that it can't import right now unless you tell it to discard its logs, which is an existing thing you can do in ZFS, like if you lose a log device. And then the big difference is that your ZIL blocks are actually stored in the shared log pool, right? All of the ZIL chains are stored in this shared log pool, and that's where all that data gets persisted. So you can create a client pool from scratch, or you can import a client pool as so that it becomes dependent on the shared log pool. So here you can see what a creation looks like. There's a new -L flag that you provide the name of the shared log pool, and then client pool name and then disks just like usual. And here you can see what it looks like. You have a client pool with its drives, and then it has a shared log entry, and then the name of the shared log pool that it's actually using to provide slog capabilities. And import looks very similar. You have to import with the -L flag as well, and you also need to provide -M to tell it that you're discarding your existing logs. You won't be keeping that data around because your ZILs are now stored on the shared log pool. That's not a problem in normal operation, because if you did a clean export with your file systems mounted, all your ZIL chains will be empty and nothing will be lost. So you just need to make sure to do that before doing the import to make it use a shared log pool. So there's a little bit of a technical issue with what I just talked about. And it's that the ZIL headers for the file systems are now pointing into the shared log pool. And that's where the actual blocks are stored on disk. So does that mean that we have cross-pool block pointers? Are we now, like, do we have block pointers on disk now that actually point to a different zpool? Is that really something that we want to have to deal with and like try to understand from the file systems perspective? And then another really big issue is the ZIL claim process that I talked about. When you import the shared log pool, which has to happen before you import the client pools, how does it know where all the ZIL chains are? Because we may not have been able to persist the allocations onto disk. We may not know where that data is stored. So how do we do ZIL claim? How do we find all of these blocks so that we can actually reliably start doing new allocations without trampling on this important data? So we need some sort of solution to solve these problems. And that solution is the chain map that I mentioned earlier. Fundamentally, the chain map is a map from a file system or an object set to a ZIL chain. And specifically to the first block in the chain, just like a ZIL header would be in a normal storage pool. In memory, the chain map is an AVL tree of AVL trees, where the first AVL tree is all of the different client pools that are using the shared log pool. And the second, the AVL trees within that are all the different file systems within a given client. And in the nodes of that AVL tree, you have these pointers, you have the actual block pointer to the first block in the ZIL chain. The on-disk format is ZAP, where the key is the pool GUID and the file system ID, and the value is the block. And so this data structure is created when you create the shared log pool and populated as part of normal operation. So let's talk a little bit about that. So let's talk about first the case where you're creating a new file system. So you have a new ZIL that's about to be created. We need to create the new chain. We need to store it in the shared log pool. And so when you create the new file system in the client, you add an entry to the chain map for that client. And then you allocate the first block in the shared log pool, and you point the chain map at the first ZIL block. You have to pre-allocate the first block of the ZIL so that it knows so you actually have a starting location for the chain, so that we can do the recovery process. Now, okay, you've got your ZIL. Now you have, how do we add new blocks to this chain? How do we do our actual ZIL writes? So synchronous write comes in. We need to allocate a place for it in the shared log pool. So we just append it to the chain the same way we would with a normal ZIL write. None of the actual logic here changes, except that the allocation takes place in a different pool than it used to. You still update the last ZIL block to point to the new one. You still do the allocation. You still put the data where it used to go. It's just happening in a different storage pool. So we've got the data. It's persisted in the ZIL block. And now it's time to sync out the TXG that the write is actually going into. So now we need to actually do the step where we move the head of the ZIL forward into a later point in the chain. So after the transaction group syncs in the client, because remember, these are two different pools and they have their own sets of transaction groups happening at different times. So after the client syncs its transaction group, it goes and gives a bunch of updates to the chain map. There's a new data structure in the client called the SPA ZIL map that stores all of the updates that it needs to make to the ZILs in this transaction group. Just a mapping from file system to the new ZIL block that the head needs to point to. And then once the chain map has been updated to point to the new location, we can issue freeze for the ZIL blocks just like we would before. The next case is where we're removing a ZIL. We're deleting a file system. We need to free all of the blocks in the chain and get rid of them and remove the chain map entry. And that happens pretty straightforwardly. So again, after the transaction group syncs in the client where we deleted the file system, we update the chain map. There's a new data structure called SPA ZIL deletes. That's just a list of all the deletions we're doing in this transaction group. So the transaction group syncs out, we apply the list of deletes, and then in the shared log pool, we go through the chain, free all the blocks, and then delete the entry from the chain map. Let's talk about ZIL claim, the recovery part of the process, or the first part of the recovery process. So after a crash or a power outage, we're importing the shared log pool again. And when we import the shared log pool, now we have the chain map. And so we iterate over each client in the chain map, and we iterate over each file system for each of those clients, and mark each of the ZIL blocks in the chain as allocated. And so that way the shared log pool is able to do the same sort of ZIL claim process that the clients did without actually needing to have their file systems. It just has their ZIL chains and it has pointers to all of them. Then ZIL replay is still deferred until the clients are actually present. Once the client pool is imported and it's found it's registered itself with the shared log pool, then for each of its file systems, it'll go to the chain map and pull the head of its ZIL chain and replay all the records in the chain, just the same way it would before, except all the IOs are going to this new storage pool. But there's a little bit of a race condition here that you might catch if you're a little bit tricky. So I talked about what happens if you delete a file system, which is that after we sync the transaction group in the client, we go and update the chain map and free all the blocks in the shared log pool. What happens if we crash after we sync in the client, but before we sync in the shared log pool? So then the chain map entry will still be present on disk and all the ZIL blocks would still be present on disk. And now we would leak that space if we didn't have some way to clean that data up. And so the solution there is that when you import the client pool, when we're iterating over the chain map entries for that client, any entries in the chain map that don't have an actual corresponding file system in the client pool, we immediately clean those file systems up. We remove their chain map, clean up all their ZIL blocks, and prevent that space from being leaked. So you do leak it very temporarily, but only until you start importing your clients again. So it's a short-term problem that will resolve itself. Eventually, when you're moving your pool from system to system, or you're done with a given storage pool, you have a deregistration process where you're removing a client pool from the shared log pool. And as part of that, we need to clean up all of its chain map entries. So we go over all the different file systems in the client and free each block in the chain just the way we would for each of them if we were deleting that file system. We mark that the client pool is no longer dependent on the shared log pool. So now it can be imported freely without the shared log pool. And then this is all done as part of an export process. So the next time it comes back in, you can import it normally and it'll start doing its slog or ZIL allocations wherever it normally would. But sometimes things go wrong. And so you might have a case where a deregistration didn't happen. Maybe you moved a pool without remembering to do deregistration. Maybe a pool got destroyed by some sort of incident. And by whatever mechanism, you have this pool that never got deregistered. So there's a new command in ZFS that serves as a backup for this. And it's basically a garbage collection process. And the idea is that you issue this command to the shared log pool, and it will iterate over all of the clients that aren't currently connected to the shared log pool. And for each of those clients, it'll do the cleanup process and effectively forcibly deregister the client. And so here you can see what that looks like. So let's say we have this client pool that is a client of the shared log pool, and we export it. If you issue the new command, which is called zpool recycle, on the shared log pool, it'll go through all of the clients that aren't connected to it and do the cleanup. In this case, you can see there's a -n flag. That's the dry run flag, which we use in a lot of other places in ZFS. And so that'll actually tell you which pools are going to get cleaned up without cleaning it up. So that way you can make sure that only the data that you want to get deleted is actually going to get deleted. And so that's the other mechanism that we use to make sure that space isn't leaked if something goes wrong and you happen to lose a storage pool. Finally, eventually you may want to delete your shared log pool. You're not allowed to do that if there's any clients currently attached to it, because they are busy using that space. It's a storage device for them. You're not allowed to move it out from under them. Similarly, you can't export the shared log pool while a client is running. So if you try to do it, it'll give you ebusy and tell you that you're not allowed. But if all the clients are disconnected or destroyed, then it'll go through, delete all the chains, free all the blocks, mark itself as destroyed, just like a normal pool would. Any clients that do still exist, if you want to import them again, they're going to need to discard their logs. So here you can see sort of the normal case where you destroy all your clients and then you destroy the shared log pool, and it looks just like destroying a normal pool. And then on the right, you can see the case where one of the clients was only exported and not destroyed. And in that case, if you want to re-import the client, you have to discard the logs. But again, clean exports that happen as part of normal operation with all your file systems mounted won't have anything in your ZIL chains. So an import discarding your logs won't lose any data for you. So that's how shared log pools work. Let's talk now about one of the important things that we wanted to preserve with this, which is performance. And a big caveat at the start is that if you aren't using shared log pools, you won't notice a change when these bits integrate. Comparing before and after for using slog devices or embedded slogs or no slogs, there's no measurable difference in performance. All of the code is gated behind checks that you're using the shared log. So there's no difference for pools that aren't using shared logs. If you are using a shared log, compared to what it would be if you had those slog devices as dedicated slog devices for the pool, you get about 98% of the throughput in terms of synchronous write operations. I tested this a bunch of times, running a bunch of different workloads with a few drives for the normal data storage for the pool, and then a few drives as the slog devices, either directly attached or configured in a shared log pool and attached that way. And the difference was within 2% for almost all of the test cases that I ran. There's one caveat, which is that if you have a lot of different file systems issuing synchronous writes at the same, or getting synchronous writes at the same time, the performance penalty got about as high as 7%. And the problem there is basically that the SPA ZIL map data structure that I mentioned is being accessed by all of these different file systems as they receive these updates. And as the ZIL chain wants to move through, you get all these different things trying to update it at the same time. This can be improved in the future by minimizing what the mutexes need to cover, using more advanced data structures, making other clever tweaks. But for first pass implementation, 93% throughput in the worst case scenario seemed like a pretty good result to me. So that's what it is right now. There are a couple of caveats with this work, a couple of restrictions associated with it. One is that you can't re-GUID client pools. This gets a little bit thorny because you need to try to synchronize the update between the client and the chain map. And that is technically tricky, even if you try to use something like a ZIL on the shared log pool side. So that's not allowed. Checkpoints are also forbidden in the current implementation. It doesn't really make sense to do checkpoints for shared logs, but it does make sense to do them for client pools, and it will probably get done in the future. But in the first pass, you're not allowed to take checkpoints of client pools because it was somewhat technically complicated to implement. But that work will probably be done in the future. As for what's available right now, there's currently a pull request open on GitHub. I would absolutely love if people took a look at this pull request, whether that's because you're interested in the technical parts of the code and you want to comment on that, or if you have use cases in mind and you want to see how well this will work for your use cases, or you're concerned about the effect this will have on other parts of the system or other features that you're working on. please take a look at the pull request, get involved, comment. Or you can reach out to me, at drinks after, at the hackathon tomorrow, or I'm available on IRC, Slack, email. I'm easy to find on the internet. And with that, does anybody have any questions for me?
Full registration from the shared, can you SQL detach the shared log to gracefully make it not part of the shared log anymore?
So the way that it works right now is basically that you have to do as part of export, but it might be possible to do it as part of a different operation like zpool detach. The problem is basically synchronizing the cutover from all of your ZIL chains being stored on one device to stored on another device, because we want to avoid the cross pool block pointer problem that I mentioned, and the trickiness that that creates. So it might be possible to do as part of zpool detach, but it would have to be like a weird zpool detach that forces all of the data out of all of your ZIL chains and then causes all of your ZILs to get recreated. Yeah, you have to kind of quiesce everything in order to make this happen. So right now it's like an export process, and then you do, well, on import, you would come back with normal slug devices.
What's the resulting size of the slug per pool? You showed 240 as I recall, but is it divided equally? Is it something else, or do you specify as a user?
Yeah, so the way that the storage is divided up among the clients is basically that all of them just get equal access to the space. There's no, right now there's no quota system or anything controlling which one gets which amount of space. And part of the reason for that is that by and large, the constraining factor on slog devices is not the amount of storage that they have, but instead how quickly they can respond to IOs. The amount of dirty data that you end up with in a slog device doesn't usually get that big for a given storage pool, because data is only stored on it until transaction groups manage to sync out. If it's important to some use case that we be able to have some sort of quota system, that would probably be possible, where you could have, checking in the shared log pool for how many blocks have been stored in it, and then make the given clients delay until some of their space has been cleaned up. But there isn't any mechanism like that right now.
Yeah, you mentioned a couple of cases where you need to import with the discard logs flag, and that in a lot of those cases you probably would have done it with export, or there wouldn't actually be any data that's discarded there. I was wondering if there's some way that we could detect that that was the case, so that you don't have to use that scary flag. So there was this kind of scary to be oh, well, I'm discarding the last few seconds of operations, but I'm pretty sure that I cleanly exported and there are none.
Yeah, so there isn't currently a mechanism like that, but it's definitely possible to implement one where if you do, if you're doing an export and it's, after you finish replaying a ZIL chain, we could maybe have some system to detect as part of that, oh, we are doing an export, we've emptied this ZIL chain, there's no dirty data in it right now. Let's mark the ZIL chain as actually being empty in some special way, like storing a whole block pointer or something like that in the ZIL header. And maybe by doing that, we could, and if you did that and had all of your ZILs marked that way, we could detect when you're trying to do the import, whether anything was actually going to be lost.
Yeah, kind of along those lines. If you'd like to get a message back, you wouldn't use the flag, and might tell you, I can't do it because you have dirty data in client X or something like that.
Right.
Would be nice to see. And kind of related to that, what message do you get when you try to destroy a slog pool that has active client?
In the same way that you would if it had active mounts and locks held, you get busy.
You get busy. Do you get any indication busy because these clients exist sort of messages?
Not right now. So part of the problem there is that the mechanism for returning errors from the kernel to user land is a little limited, but we could have something in user land that was if we get busy, check if this is a shared log pool. If it's a shared log pool, get the list of registered clients and display that as part of the error message.
Do you think this opens the door anymore to a different allocation, algorithm for specifically for the log pool, a lower latency allocation?
Yeah, I mean, so there were recently changes made to ZFS, I know, to make it so that you can tune allocators more easily with parameters and stuff like that. And related to that, we might want to have something where you can have per pool allocation schemes, where I don't know if we can do that today, but if you could, having something like a first fit approach specifically for the shared log pool to minimize latency would make a lot of sense. That would probably be part of a separate, Don might have a comment on that.
Yeah, we had done that at a previous company, but we were first fit, it's like, you don't need to worry about. That's it.
Right.
I had a question on the testing it, there's like a spa freeze and it's still test, did you do something like that?
Yeah, so the way that this was tested was so first there's a bunch of new tests in the ZFS test suite to test like the basic stuff, like make sure you can't destroy a pool while things are attached and all that kind of stuff. And then there's also changes, I think I made changes to Z-test. I don't remember if those are part of the PR, I need to check. But there are changes that like create, that use shared log devices and stuff like that. And then for the performance testing, the ZFS performance test suite now lets you create shared log pools instead of using slog devices. You can specify like what kind of slog you would like to use when you're doing synchronous write testing.
Yeah, I was thinking of the test, I think Neil Kerman did it, but basically you could freeze the spa, so it's not going into the transaction. It's just like only in the ZIL, and then you can replay it, compare it, and it's like, you did the data persist through the ZIL.
Yeah, I didn't run any tests with that feature specifically, but it sounds like that would be good, something potentially good to add to like a Z loop run or something like that.
Well, does the shared log pool know that the client has not done a mount? So the case where, for example, like, you know, we did the claim, but we haven't done the replay because maybe the file systems are set, you know, to not mount automatically. Does that log pool know, so that going back to the case of like doing the dash n, that would be an instance where you wouldn't want to do the dash n because you never did the replay.
So the shared log pool doesn't know what client file systems are mounted or anything like that. That information is purely stored on the client side, and the freeing purely happens, like the updates to the chain map are purely client driven. So it doesn't know whether or not the client has mounted any of its file systems or done replay or anything like that. So that is definitely something else to think about when it comes to like exporting with deregistering and importing, discarding your logs. Some of this is solvable. Some of it's very tricky to find ways to fully protect the user. And I don't know, I would be happy to talk to people about possible solutions for some of these problems because I don't know if all of them are solvable.
Because in case of replay, you should already have log recreated, so you could flush the chain and you record the chain is now empty and you could safely drop it on that. It should be doable.
Yeah.
I have other thoughts, like first during reclaim command, you could specify for which pool you would like to reclaim. If you store information not only read but also full name, it would be much more manageable. I think you could just know which pool has gone and which is not important.
Yeah,
It would be more convenient to see that. And with some command, maybe release inventory of what chain, what shipping do you have, which are currently connected, which are not, manage that.
yeah.
I think I was thinking, I don't know about implementation, how quick that would be, but if you have, I'm thinking whether it could represent log pool with as another special kind of VDEF. So you could use add, remove command, and other, because special like -L argument to import is pretty ugly and special thing, like in this case.
Yeah.
You don't want to import export pool for management. It should be much more smooth and another special VDEF. Of course, it would require a number of hacks to make it special, but we already have like indirect VDEF, which is not visible, but it's present there as well. Kind of opposite case of visible, but not there. But
Yeah, so this was something that was considered. So first question first about the name versus good thing. It's definitely possible to add like a good mapping in the shared log pool with the names of the clients or like the last name that they were registered with. And that's something that I can implement as part of the initial draft. It shouldn't be that much extra work so that you can use the name as part of the recycle command. When it comes to having it be like as a Z pool add or a Z pool attach or something like that, instead of an import export thing, The problem again is sort of the synchronization of like, when do we make it so all of the ZIL chains point to the new device rather than being stored on the current device. And if you're doing it as part of adding a new VDEV, you're doing it as part of normal pool operations, which means that you have like IOs to your existing slogs already ongoing, and you need to find some sort of way to migrate the ZIL chains over. And it's not impossible to do, but it was sufficiently tricky that I decided that the cleanest way to do it was as part of the import-export process.
I think it shouldn't be that complicated. If you just in a root of your blockchain, you report whether this specific blockchain belongs to the shared pool or it's your local. If it's your local, behave the same as any other blockchain with block pointers and everything. And if it's shared pool, then it's shared pool and works through the blockchain mechanism you described. But that way you could easily combine both, just one data set which is not mounted can live happily on your local pool, another data set that was that last synced and created log after the shared log was created, when you live shared. You may happily coexist those, you can remove and delete each of those dynamically. I don't see a problem, and I think it much more convenient than global switch.
I think one of the problems with it is that you have to, so if you just did it as an attach like that, then coordinating when a given file system would switch over to the new shared log pool is an issue, because you would need like you have to empty the ZIL chain for that file system in order to switch it over. And so we would need some mechanism to like force a given file system to empty out its chain and then recreate its ZIL on the new system, unless all of your existing file systems would stay on your existing slog devices and only new file systems would get slogs on the new thing. Unless you tried to like update the tail of the chain and have that have a special marker to point into the shared log pool. That might be technically feasible, but it seems like it would be a little bit challenging.
Well, I think that already happens when you do normal device removal. Like if you do device removal, you have to get the ZIL chains off. I think that might already happen, like when you're doing device removal and some other operations where it goes through all the ZILs and like discard, like gets them all gone and then it creates another one. I think it was like a
Spot reset.
Spot reset logs, yeah, exactly. Spot reset logs already does that. So you do have the case where, like you're mentioning, you might have some data sets that are in the old location and some that are in the new location, but they're all kind of like on their way to being in the new location by like discarding the old one and inserting a new one by using the spot reset logs. So that might be helpful.
Okay, yeah, I can take a look at that. Probably not tomorrow because I have other plans for tomorrow, but sometime in the near future.
With a multiple record, with a shared log pool. So this shared log pool could be a single point of failure, right? So what happens if it goes wrong?
Yeah, so if the shared log pool itself has failures, I mean, in much the same way that if your slog device dies attached to a normal storage pool, you might have to import losing your logs. And this is something that ZFS already handles. But this is part of the reason why it's recommended that if you care about your slog devices, you have mirroring or things like that. And you can have mirrors in shared log pools. They're created just the same way normal pools are. You could have them be mirrored or RAID-Z or whatever.
Okay, I saw you put it the forward, you know, 3.0, that's right.
Yeah, the example I used was Stripe, but you could use mirrors, you could use RAID-Z, you can use whatever sort of VDEV functionality ZFS has.
Really, it support any layout?
Yeah, it'll support any layout that ZFS supports right now, because fundamentally it's just a normal storage pool whose allocations are being like done in a weird way, but the backend all works exactly the same way that normal pools work.
So in your code, is there any like a fallback strategy? Like if you go wrong, you go back to the like you the data for itself to store a ZIL record?
You mean like if the shared log pool faults?
Right.
Right now, if the shared log pool faults, the client pools are also going to fault. Because one of what is effectively a device of theirs, or what is functioning as a device of theirs, is faulted. And so they'll go into a faulted state. It would be possible to instead have the data store, like instead have it go to a failback mode where it would try to store the data locally. But you need to do something about the ZIL chains that are already on the device. And you would either need to like recreate those locally or do some other sort of mechanism. So there's nothing like that right now, but it's possible that you could make a change that would have a more graceful fallback mode.
Yeah, because we run a bunch of servers and time to time when a slot we try a problem,
Mhm.
you will be in a mirror case. That problem basically the equal IO which is stored.
Mhm.
That's what we observed. Probably since that has been improved. At least a few years back, we got this problem, frequently.
Mhm.
So that's why I asked you this question.
Yeah.
If something goes wrong, is there any way to make it keep going?
Yeah. No, that's a good question. I think that's something that could use more work, probably, either as part of this PR or as a separate mechanism.
Thanks,
Cool.
Paul.